So, in the last class we saw how the entropy changes are calculated during an irreversible process, and most importantly we saw that interdiffusion is an irreversible process. It basically drives the system from non-equilibrium state to an equilibrium state. So, how do we define an equilibrium state? We have seen before, in terms of entropy and internal energy we can define the equilibrium state. So, at constant internal energy and volume, the equilibrium state corresponds to the maximum entropy, or at constant entropy and volume, the equilibrium state corresponds to minimum internal energy. Okay. So, that means to define equilibrium state in terms of S and V, we need to select the independent variable. So, in terms of S we need to select u and v as independent variable, or in terms of u we need to select s and v as independent variables. Now, this pair of variables are not really convenient to handle. Imagine you are carrying out certain process in which you want to keep volume constant and vary internal energy systematically, or you want to keep volume constant and vary entropy systematically, right, or you want to control the entropy, which looks really difficult, right. So, these are not really convenient variable to handle, and so we need to define the criteria of equilibrium in terms of variables which are easily manageable, which are easily controllable by us. Which are those variables? Temperature, pressure and volume, more specifically temperature and pressure, right. And so, we need to define other state functions which can define the criteria of equilibrium in terms of these variables. Okay, and that is how the next state functions are defined. There are three more state functions: enthalpy, which we defined as U plus PV, Helmholtz free energy, which we define as U minus Ts, and Gibbs free energy, which we defined as H minus Ts. So, let us analyze them one by one. Let us try to see what independent variables we can use in order to be able to use this new state functions for criteria of equilibrium. For example, if z is a function, let us try to derive the equation in terms of dz equal to dou z by dou x at constant y dx plus dou z by dou y at constant x dy. So, we know x and y are here independent variables, right. So, if we take the differential of h here, dh is equal to du plus p dv plus v dp, and by the combination of first law and second law we know du is equal to t ds minus p dv plus p dv plus v dp, and so dh is equal to, this gets cancelled, t ds plus v dp, right, which we can write in the form dou h by dou s at constant p ds plus dou h by dou p at constant s dp. So, by definition the partial of h with respect to entropy becomes T, or partial of h with respect to pressure becomes volume V, right. So, we know h can be expressed as a function of s and p, and we can show then at constant s and p equilibrium state corresponds to minimum enthalpy. Okay. So, we got a criteria of equilibrium in terms of H, but again this is not very convenient. So, let us try to figure out what happens with A. So, if you take the differential of A, you have du minus T ds minus S dt, substitute for du, T ds minus P dV, T ds minus S dt is equal to, it cancel, minus S dt minus P dV, and so we know that A can be expressed as a function of T and V, and with this we can express the criteria of equilibrium. So, at constant temperature and volume, equilibrium state corresponds to minimum in Helmholtz free energy. So, let us try to apply it to G also, since G is equal to H minus T s, dG is equal to dH minus T ds minus S dt, and dH we know is equal to plus T ds plus Vdp minus T ds minus S dt, and so dG is equal to minus S dt plus Vdp. So, now we have a state function which can be expressed as a function of T and P, and the criteria of equilibrium becomes at constant T and P, equilibrium state corresponds to minimum in G. G is the Gibbs free energy. Okay. So, now this is convenient. We have Helmholtz free energy. If we want to use temperature and volume as the independent variables, we can use Gibbs free energy to define criteria of equilibrium if we want to use temperature and pressure as independent variables. So, both are important, right. Through the experimentalist perspective, as an experimentalist we usually handle temperature and pressure as independent variables, right. For example, when we carry out isothermal diffusion experiments or annealing at constant temperature, right. So, we are defining, I want the annealing temperature to be, let us say 800 degrees centigrade, and most of the time we assume the pressure is at 1 atmosphere, right. So, that means we are using temperature and pressure as independent variables. So, we need to use Gibbs free energy as our criteria for equilibrium. So, for experimentalist, Gibbs free energy is a very important state function, but through the theoretician's perspective they would like to use Helmholtz free energy, because they would like to keep volume constant, and the reason is by keeping volume constant the energy levels are fixed, right. So, the theoreticians will use Helmholtz free energy A for the criteria of equilibrium, right. So, for this class we will most of the time using temperature and pressure as independent variables. So, we will now focus on the Gibbs free energy. Okay. So, in terms of all these variables, now we have developed the what we call as equations of state, right. So, in terms of internal energy or entropy, we define du is equal to T ds minus P dV, dH is equal to T ds plus V dP, dA is equal to minus S dt minus P dV, and dG is equal to minus S dt plus V dP. Now, so far we have assumed constant composition throughout our analysis. We did not let the composition of the system change, but what if the composition changes? So, we know that all these state functions u, s, h, a, g, they are all extensive properties, which means they depend upon the size of the system. So, when we allow the change in composition, then we need to also take into account the number of moles of each of the species. So, for example, instead of expressing G as just a function of T and P, we need to write G as a function of T, P and number of moles of all the components, right. So, the differential of G is expressed as dou G by dou T at constant pressure and composition dt plus dou G by dou T at constant temperature and composition G by dou P dP plus partial of G with respect to number of moles of I at constant temperature, pressure and all other number of moles partial of G with respect to number of moles of J at constant temperature, pressure and all other number of moles I naught equal to J and so on. And now, this partial is an important quantity, right. So, what is this partial basically? It expresses the change in Gibbs free energy because of addition of 1 mole of I at constant temperature, pressure and constant number of moles of other species, and this is called as chemical potential. Right. So, the chemical potential of I is defined as dou G by dou Ni at constant temperature, pressure and all Nj's not equal to I. Now, have to remember that chemical potential is also a function of composition, right. So, when you make this addition of 1 mole of I, the composition of the material should not change. So, when we define this chemical potential, the addition of 1 mole of I is done to a large bulk of the material such that addition of 1 mole of I does not change the composition significantly. Okay. You can express this either in terms of per mole or per atom. So, if Ni is number of moles, this is joules per mole. If you express in terms of atom, how much Gibbs free energy changes by addition of 1 atom of I at constant temperature, pressure and constant number of atoms of all other elements, that is then it will be joule per atom. Okay. And this is an important quantity in our class of on interdiffusion. As I mentioned in the last class, the fundamental driving force for diffusion is the gradient in chemical potentials. So, you need to understand this. Now, with this we can modify our equations of state to take into account the changes in composition as dG is equal to minus S dt plus V dP plus mu I dNi, and the summation goes over all the components I equal to 1 to n. So, one more thing quickly, this chemical potential can also be defined in terms of Helmholtz free energy or enthalpy or even internal energy, right. So, you in terms of internal energy you can define as change in internal energy due to addition of 1 mole of I, and we know U is a function of S and V. So, at constant entropy, volume and Nj not equal to I, or it can also be equally defined as change in Helmholtz free energy, and A is a function of T and V. So, dou A by dou Ni at constant T, V and Nj not equal to I, or change in enthalpy H which is a function of S and P. So, at constant S, P and N j not equal to I. So, now we know how to define the equation of state even when there is a change in composition. Now, this change in composition may be because of two things, right. The first way the change in composition is brought about is you allow the system to be open system. So, the mass can be exchanged and obviously the composition will change, but even within a closed system during a particular reaction or during a particular transformation, right, the composition of different phases can change, right. So, all that will be taken into account if we apply this new equation of state which considers the chemical potentials. Okay. So, now with that we also know the criteria for equilibrium in terms of Gibbs free energy. We will now next move to the stability, because that is our main interest, to define the stability of different phases. Okay. So, for example, if I consider a process at constant T and P, I know I need to use Gibbs free energy as the criteria for equilibrium, and if I tract Gibbs free energy as a function of some arbitrary unit, for example, atomic arrangement. So, if I continuously change atomic arrangements at constant T and P and see how the Gibbs free energy changes, I may get some variations schematically like this. Okay. So, I need to define now which is the stable state. Right. So, how many equilibrium states are here? Right. So, we know for equilibrium the Gibbs free energy has to be minimum. So, locally we see there are 3 minima, right. So, let us denote them by A, B and C. So, there are 3 equilibrium states A, B and C. How many stable states are there? Right. So, there is only one stable state, and which corresponds to the global minimum in the Gibbs free energy, right, and that is B. So, the stable state here is B. A and C are equilibrium states, right, but they are not stable state. The criteria for stability is the Gibbs free energy has to reach the global minimum, and global minimum here is B. A and C are referred to as metastable state. They are called metastable because during a particular process or during a particular transformation, since the Gibbs free energy there is minimum, those states can be realized temporarily. Now, the temporarily time frame will depend upon the kinetics, right. So, for example, what is the example that you know of a metastable state? Diamond. Or in steels we have martensite, right. So, typically iron at room temperature will exist as BCC, or mild steel the low temperature stable phase is BCC or alpha. But if you quench it fast, you see austenite, instead of transforming to alpha, it will transform to martensite, and that martensite is a metastable phase. So, which means that over certain amount of time it will eventually transform to BCC, but since the kinetics are very slow, so it takes very long time. So, you feel as if the martensite is a stable phase, that is why it is called a metastable phase, but ultimately it will transform to the final equilibrium state. Okay. So, that is the difference between stability and equilibrium. Equilibrium, we just say that Gibbs free energy is minimum at constant T and P. For stability, the Gibbs free energy has to reach global minimum. So, the phase which has the least Gibbs free energy among all possible phases will be the stable phase. Now, there may be more than one phases which have the same Gibbs free energy and which happens to be the global minimum in the Gibbs free energy. In that case, both the phases are stable. So, we say that the two phases coexist in equilibrium. Okay. So, now let us see what drives the transformations, and for that we need to analyze the Gibbs free energy as a function of temperature and pressure. So, first let us try to look at how the Gibbs free energy varies, first with temperature at constant pressure, then with pressure at constant temperature, and then we will see if we vary both how the Gibbs free energy changes. Okay. So, let us first try to look at how the Gibbs free energy changes with temperature at constant pressure. We know that dG is equal to minus SdT plus VdP, and to start with we are analyzing single component systems, which means the composition is constant. Now, the single component system means the system contains only one component. That component may be a pure element or it may be a chemical species or a molecule which does not dissociate over the range of temperature and pressures that we are studying. For example, water, if you want to analyze the phase transformations in water, how it transforms from ice to water, water to vapor, and there is no reaction occurring or no decomposition of water occurring, then we use water as a single component system. Okay. So, since at constant composition, so we do not need to include mu I d and I terms, and we want to analyze how the Gibbs free energy varies with temperature at constant pressure. So, what will be the slope of the plot? Slope means variation of G with respect to temperature at constant pressure. From this equation, the slope should be equal to minus S, and entropy is always positive, right. So, the slope of G versus T curve has to be negative. Now, what will be the curvature? Curvature is the second derivative, so that is basically dou S by dou T negative, and what is dou S by dou T? Minus Cp by T. Again Cp is positive, T is positive always. We are considering, remember, the temperature in Kelvin, the thermodynamic temperature scale. So, temperature is always positive, and so the curvature should also be negative. So, the schematically the plot will look like this. So, as the temperature increases, Gibbs free energy decreases. Gibbs free energy of a phase or of a system decreases with temperature. What about variation of G with P at constant temperature? So, again if we try to see the slope dou G by dou P at constant T from the equation of state here, we know it is volume, and volume is always positive. So, the slope should be greater than 0, and the curvature, which is the second derivative, should be dou V by dou P at constant T. Is negative or positive? Negative, right. So, at constant temperature, if you increase the pressure, the volume will decrease. So, the dou V by dou P is negative, and so the curvature is less than 0. So, if you try to plot G versus P at constant T, schematically it will have a shape something like this. Now, let us try to analyze the phase changes in the context of Gibbs free energy change, right. So, let us consider transformation of solid to liquid. So, let us denote the Gibbs free energy of solid as Gs, Gibbs free energy of liquid as Gl. So, if we plot at constant pressure, if we plot G versus T, if we see how the Gibbs free energy of solid and liquid changes. So, obviously, I know the kind of shape of the two curves. So, I draw one curve for solid, one curve for liquid. Okay. The one that I drew first is solid and the second one is liquid. Why? How do you know? From the slopes, right, because we know the slope of G versus T is minus S, and entropy is a measure of disorder, right, and we know the solid is more ordered than liquid, right. So, the entropy of solid is lesser than liquid. So, the slope of G versus T curve is higher negative for liquid than for solid. So, they will intersect at some point, and this is the equilibrium melting point Tm. So, at any temperature below Tm, we know the Gibbs free energy of solid is less than that of liquid, and so solid is stable.
Is there any difference between equilibrium melting point and melting point?
Equilibrium means both solid and liquid are in equilibrium at that time. So, like here, so I will talk about it now. See, at T equal to Tm, we have the Gibbs free energy of solid is equal to Gibbs free energy of liquid, right. So, at exactly Tm, T equal to Tm, at this particular pressure that we are considering, the Gibbs free energy of both solid and liquid is same. So, both are stable phases. That is why we say that solid is in equilibrium with liquid, and this is denoted as equilibrium melting point. Okay. So, at T equal to Tm, solid in equilibrium with liquid. At T greater than Tm, Gl is less than Gs, and so liquid is stable. Okay. Suppose we could cool the water below T equal to Tm, let us say at this temperature, let us say at T1. So, we know at T1 G liquid is greater than G solid, right. So, liquid is an unstable phase. So, it has to transform to a stable phase, which is solid. So, liquid to solid transformation will occur irreversibly. So, there is an irreversible freezing of the liquid, because it is associated with decrease in Gibbs free energy, right. So, if you calculate delta G for this change liquid to solid here, it will be final state minus initial state, Gs minus Gl is less than 0. So, the change decrease in Gibbs free energy is a driving force for this freezing here. Similarly, if we could heat this solid to a temperature greater than Tm, we know that now solid has a higher Gibbs free energy and it has to transform to liquid. So, there will be an irreversible melting. So, delta G for solid to liquid here will be GL minus GS again less than 0, and so at T2 there will be an irreversible melting. But at exactly T equal to Tm, both Gibbs free energies are same, so there is no driving force, right. So, both phases are stable. So, by any chance if you start with completely solid phase and if you heat it to T equal to Tm and stop there, what should happen? Exactly at T equal to Tm, the solid will remain as solid, because there is no driving force. Only when you try to increase the temperature, some solid will transform to liquid. Similarly, if you cool the liquid from T2 slowly to temperature Tm and stop there, what will happen? The liquid will not immediately transform to solid. If you stop, then the liquid will remain as liquid at Tm, because liquid is also stable at Tm. Only when you try to cool further, then the liquid will transform to solid. Okay. So, exactly at T equal to Tm, delta G is equal to 0, and at constant T and P we can write delta G as delta H minus T delta S, and so delta S is equal to delta H over Tm. So, this T is Tm. There is an equilibrium melting point or equilibrium melting temperature at a given temperature. If I change the pressure, how the equilibrium will shift, right. So, in other words, if I change the pressure and if I still want to maintain the equilibrium between solid and liquid, which way the temperature should change. Okay. So, let us try to analyze that. So, at equilibrium we know that Gs is equal to Gl. Now, we are changing the state, but we are still maintaining the equilibrium between solid and liquid. So, whatever change in Gibbs free energy of solid, the same change in Gibbs free energy of liquid should accompany, right. So, we can write dGs is equal to dGl, and if we substitute for dG, we know minus SS dt plus Vs dP is equal to minus S L dt plus V L dP, and if we rearrange, we write dP by dt is equal to delta S by delta V, and at equilibrium we know delta S is equal to delta H by T delta V, right. So, this is the Clausius-Clapeyron equation. So, now more specifically we denote this as dP by dt equilibrium. Why? Because we are observing if I change the temperature a little bit and still maintain the equilibrium between the two phases, how much change in pressure has to be carried out, or if I change the pressure a little bit and still want to maintain the equilibrium between the two phases, or which way the temperature should change. Now, this we analyze for solid to liquid or liquid to solid, but this is equally applicable for any transformation. So, if we know delta H and delta V, we should be able to know which way the temperature should be shifted. So, for example, let us try to analyze the melting of ice, right. So, for melting of ice, we know ice to water transformation, what should be delta H? H water minus H ice should be positive or negative? Positive, right, because higher temperature phase will have higher enthalpy, and that appears in the latent heat of fusion, right. So, heat is absorbed because water has higher enthalpy. So, this is positive greater than 0. What about delta V? Molar volume of water minus molar volume of ice. It should be negative or positive? Normally for melting the volume will increase, right, because liquid phase will have higher volume than solid phase, right. But for water it is reverse, right, because ice has lower density than water around near to 0 degree Celsius, right. So, because of that the melting will be associated with reduction in volume. Water will have lower volume than ice, and so delta Vm is less than 0. So, basically for melting dP by dt, right, for melting of ice is negative, which means if I increase the pressure the equilibrium melting point should be reduced, and this is the reason why ice skating becomes possible, right. When the skater is skating there is certain pressure applied on the ice, and because of that pressure the melting point which is in contact with the skate comes down, and so the water melts and there is a thin layer of water that forms between the ice and the skate, and it helps the skating, it acts as a lubrication. What is another example? You can also consider the water to vapor transformation, right, or boiling of water. Now, here what will be delta H? Obviously positive because water converting to vapor, vapor has higher enthalpy. What about delta V? Should also be positive, obviously the vapor has higher molar volume than water, and so dP by dt is greater than 0. So, if we decrease the pressure the equilibrium boiling point should decrease, right, and that is the reason at higher altitude the boiling point of water comes down, right. So, if you try to cook rice at higher altitude it is difficult, right. At higher altitude the atmospheric pressure is lower, and so the equilibrium boiling point of water reduces. If you try to cook rice in open pot the water will start boiling before the rice is cooked, right, and that is why you have to use pressure cooker, right. In pressure cooker you can maintain the pressure near to 1 atmosphere and then easy to cook rice. Okay. So, these are the examples. This is a very useful equation because we can use this to develop phase diagrams. So, what we are doing here basically is tracking how the equilibrium shifts if I make some changes in temperature or pressure. So, if you plot the locus of pressure and temperature at which the equilibrium exists, you are basically plotting the boundary between the two phases, and that is what you need in the phase diagram, right. So, for example, you can consider the phase diagram of water. So, for single component system we draw the phase diagram as a pressure versus temperature. So, for water for example, this is how the phase diagram for water looks like. So, there are different regions, this is solid ice, this is liquid or water, and this is gaseous region or vapor. Now, if you look at this curve, let us call this OA, it is the boundary between solid region and liquid region, and exactly along AO the solid and liquid two phases exist in equilibrium, right. So, this is basically the equilibrium melting. Now, you can see from the Clausius-Clapeyron equation that we seen earlier, right, dP by dt is negative for solid to liquid transformation in water, and so this line has a negative slope. But solid liquid to vapor or boiling, which is this line, let us call this OB, it has a positive slope. Similarly, solid to vapor has a positive slope. Now, you can see these three curves intersect at one point O. That means, at this point all three phases coexist in equilibrium, and this is the triple point. So, at triple point solid, liquid and vapor, all three phases coexist in equilibrium. So, this is at around 0.0075 degree centigrade and 0.006 atmosphere. Okay, so, if we try to plot let us say G versus T for water at constant pressure of 0.006 atmosphere, how would it be? Now, we have three phases, three possible phases. So, we need three curves. So, if we see at 0.0086 atmosphere, as we increase the temperature, what happens? First the solid is stable at low temperature, then as we keep hitting at 0.0075 degree centigrade, we reach the point O, which is the triple point. So, all three phases are in equilibrium, and then we enter the vapor region. So, basically at point O, the Gibbs free energy of solid is equal to Gibbs free energy of liquid is equal to Gibbs free energy of vapor. When I say this Gibbs free energy, these are basically the molar Gibbs free energies, right, because Gibbs free energy is an extensive quantity. So, I am talking about molar Gibbs free energies. So, the molar Gibbs free energies of solid, liquid and vapor are equal at 0.006 atmosphere and 0.0075 degree centigrade. So, I will have three curves which intersect at one point, right. So, if I draw these three curves, let us say one for solid, one for liquid and then one for vapor. So, all three curves should pass through one point or intersect at one point O, and this is the triple point. So, at temperature below this solid stable, at temperature above this vapor stable, and exactly at the temperature equal to triple point temperature, all three Gibbs free energies are equal. Okay. So, this is how we can develop the single component phase diagram based upon the Gibbs free energy changes. All right, any question? So, we will stop here for today.